Cool. So for today, we have several things. First, one announcement. On Thursday, the next coming Thursday, one of my friends and colleagues here at Stockton, and he's developing a new program here, and he wants some minutes to explain the program and recruit some people, and he needs students. So he will explain his program and what he's doing. It's related to taxes. And you might think, oh, taxes, I hate that. Right? I know, I hate it too. Especially as a foreigner, it's even worse, right? Because you have to navigate a new completely system. And if you fail, there are consequences and for your visa and everything. So, I hate it. But what he's trying to do, he did it the last year, was a program where students help other people to file their taxes and do a lot of things. And you might be thinking, well, I'm not an expert in taxes. Nobody is an expert. But, well, he is actually, because he's an accountant. He has a PhD in accounting. So he knows more and better than us how is the system and how it works. So he created like a free clinic for the community. But free requires people. So what we do is to recruit new students, right, for the program. And you might be thinking, what do I get in return? Well, you might not get money, but you get a good how can I say, a good line in your CV, right? Because if you volunteer on all these things, it looks good in your CV. If you're applying for masters, or if you're applying, or even for finding a job. Sometimes, when you volunteer your time, it might be useful for some employers to see that you actually are an active member of the community, right? So he will talk more in our next session about it, and let's see if any of you wants to join, right? So the next session, probably I will talk about stats a little bit at the end if he doesn't take the whole class. I don't know if he needs the whole class. I don't think so. He will explain briefly this probably, right? And the other thing is that, this is our last week of classes, right, in this class. So let me show you here. Calendar. It doesn't show the bar here. So we are here. We will have class on the 5th, and this week we are not going to be here because, Tuesday 10th is actually an instructional day. It's our last instructional day. We could have a class on Tuesday if you want to. I have plenty of things to talk, but I would say that you need time to finish one of the extra assignments that I just added last night. So I would say just use that time to submit that one, right? And we don't have to come to class, right? Unless, if you want to have a class, we can, of course, have it. I'm fine. I love what I do, but yeah, I would say it's better if I give you that instructional day, so you have the whole week to finish what I'm going to explain today, right? So I think it's fair, and you will have more time. Also, if you're behind on assignments, and I was willing, in theory, this one is exams, 16th, 17th. These are exams week, right here. I was thinking that we could set the deadline for everything on the 13th, if you're behind on assignments, right? If you need more time, I can give you more time up to the 19th, right? I think that's the maximum I can do, because I need to submit the grades, right? Otherwise, they don't pay me. No, they pay me anyway. But of course, it doesn't look good if they send me emails like, "Hey, where are the grades? Where are the grades?" Right? And I'm waiting on a student. I cannot do that. So I would say that the deadline for submitting everything should be Friday 13th, right? If you need more time, just send me an email. And of course, we will have an extra week right here where I can wait for you to submit any pending work, right? And that's, as I said, that's the maximum stretch I can do. I cannot do more because I have deadlines too. And yeah, and some of you might be graduating, or some of you might be actually enrolling other classes and you need that grade. So yeah. The other thing is, please remember to fill out the spot evaluation. Is right here, right on the spot dashboard. If you already did it, thank you. Thank you so much. I don't know, I don't see who did it, but if you already did it, thank you. But if you have time and you haven't done it, please fill out this spot dashboard. Very important for us as faculties, and these define many things in our career here at CSU. And the other thing is, and given that we are approaching the end of the semester, and some of you, I might see you in my next class, some of you enroll my class, some of you will enroll other classes, or I will see you around, I don't know. But most likely, I will see you again. But if you want to be in touch with me, you have my email, or you can also follow me on this social network called Blue Sky, similar to Twitter. I migrated from Twitter to here, and as you can see, I'm trying to follow some people who are doing some memes and everything, because I need to improve my memes, you know? They're very bad. They suck, you know? I know that. I know that you think about it. So yeah, I post most of the time about stats. Of course, I'm very boring. And so once in a while, I talk about politics and other stuff. But most of the time, what I do is to follow people around. As you can see, I have following a lot of people, mostly statisticians and researchers. And I have some followers, which is nice, you know. I feel like I'm the Kardashian of science, you know. It's amazing that people think that I have something clever to say and they follow me. So yeah, as you can see, this is about, I always reshare or repost things about causal inference or something like that, because I love those kind of things. So if you have an account with Blue Sky, you can follow me there. I don't use Twitter. I don't like it anymore. It used to be a nice place, but it's not a nice place anymore. And so yeah, now I migrated to other social networks. And I don't use Instagram because I don't know how to use it. I should probably record videos. I don't know how to produce videos, you know, that are fun and entertaining. I'm very boring, so I don't know. Probably my daughter would sometime teach me when she's older. She will teach me how to be a funnier guy. But yeah, so, I did tell you, in Blue Sky, you can find me as, if you have an account, as @msquared.net, similar to my webpage. I just linked my webpage to the Blue Sky server. And it's kind of easy to do that if you have a webpage with a domain. That's kind of nice. So you can find me there as @msquared.net, and you will see my posts and everything. You can follow me. You can discuss with me if you want to. It's fine. Discussion is good. And yeah. The other thing is, let's see if I have another announcement. Oh yes, grading and everything. That's more important than social networks. In this class, I didn't have time to assign more practices, and I promised more, but many things happened that didn't happen. And also, we were supposed to have another assignment number 3, but I kind of changed that into a final exam, quote unquote. It's not actually a final exam, as I said before. It's more like another assignment, and that's going to be the final activity in this class, right? And actually, I created this one, but I will give you extra points if you can improve this little this RC text, which is kind of wrong. I didn't realize there's a mistake there. If you want a space here between Q and me, you have to improve that. So if you can find a way, I can give you extra points. I know the way, but you can think about it, right? I love Keanu Reeves. I think he's a nice guy. So I always use Keanu Reeves as a meme. And I grew up, my generation grew up watching Keanu Reeves, you know. The first movie that I watched by Keanu Reeves was Dracula by Francis Ford Coppola, right? Well, directed by Francis Ford Coppola. And then Matrix, of course, and Little Buddha, and all these movies that probably you haven't watched because you are too young. But yes, I grew up with Keanu Reeves. So Keanu Reeves is now my meme, one of my most favorite memes. He's a nice guy. Okay, now I posted this last night. Probably you haven't seen it, right? And that's okay. I was expecting you to see this at 11 p.m., right? And I want to show you how it looks like. It's very similar to what we have done before. It looks exactly as another assignment. There are some questions about, I actually wanted to add more, but I didn't have time. I kind of spent more time on the second part, and which is, as I said in this file, in this new assignment or exam. I call it exam, but it's not exactly an exam. It's just like another assignment. I mentioned that this is one excuse to do another lecture, so it's more like a mini lecture on other things. Tell me.
Will you be doing like a video on this?
Yes, and actually today I'm going to explain all the exercises, so you will have everything on video. Yes, of course. Yes, the same format. It doesn't change. Oh, there's one difference. I have noticed that some of you are working in pairs or working in groups, or sometimes you solve with another classmate your assignments. You can submit these in pairs, right? So this time, if you're working with somebody, you don't have to submit two individual assignments. If you're working with your friend or something in this class, it can be only one, and just add your names, of course, so I know who is your other partner, right? But it can be in pairs, right? Yes, tell me.
So when we're editing the file, do we put our name and then put their name?
Wait, what's that?
So when we start a new art file, we put our names as the author. So
yes, in author you can put two names.
Okay.
It can be, I don't know, Pedro and Juanito, right? Could be like that, right? Yes. Yes, it supports several authors. So yeah, in Quarto you can put several authors. Yes. This part is very easy, I believe. So I want to focus more on this part. And you can go to my webpage, it's already there. So you can go to msquared.net. Well, what's the name? -squared.net. And you can see there the instructions. So during this semester, I forgot actually to explain more about repeated measures. So I added that one here. It's more like a new topic, and with some things I already did in this class. So in here, I'm explaining the data set called, and you might remember this one. I call it, I believe, the ANOVA data set. And let me show you something here. Let me just open it in order. I hate when Windows is right here. All right. Here, 1 second. So, let me just clean this because I was working on another thing with other students. Okay. I should make it probably bigger. Let's do that. Why? Some in. Why you're not doing it? Wait a second. I just need to zoom in a little bit, but I need to check. Why you're not doing it? Oh, no, that was too much. Just press. It is. It's by Windows. It's too slow today. That's magnifier. Well, I can use magnifier. Yes. Yes, I can use magnifier when I need to. But I just want you. No, it's frozen. Let me just close this. 1 second. Sorry about that. This is why I don't use RStudio for my personal work. But that's good. Remind me later. Yeah, now it's working. Okay, a little bit better. Yeah, that's better. Okay, so in this example that I'm going to provide, I'm using a data set that we used before, the ANOVA data. You might remember that this is the data set related to an intervention with older adults that I explained with autobiographical memory. Remember that I think it was in assignment number 2. We were talking about this data set, right? In this data set, we had scores, right? And about cognitive performance. And what we did was to analyze the score after treatment by group, right? We had 4 groups, right? And probably can refresh your minds right here very quickly. So in that data set, it looks like this, right? We had a score that was post-treatment and another score that was pre-treatment. Remember that the outcome was to improve their cognitive performance, right? In general, actually, the CANCOG instrument is kind of measuring. It's like a global index of basically cognitive performance in general. How good is your cognition, right, when you are getting older? That's an instrument that we use for that. And we had the variable group. You see the column there. It says group A, B, and C. And in here, I'm refreshing actually all the variables, right? I'm explaining again right here, right? Remember that group A was the group of participants with mild cognitive impairment. Group B was, they were older adults with mild cognitive impairment, but they didn't receive the treatment. In condition A, they got the treatment. In condition C, or group C, participants were healthy, but they received the treatment. And in condition D, they were healthy too, healthy older adults. They didn't have any cognitive impairment, but they didn't receive the treatment. They didn't get the treatment, right? And remember that we did a ANOVA with this, right? I believe it was ANOVA or regression. I don't remember right now. I think it was ANOVA. And we saw that the intervention did work, right? Remember, they told you, hey, well, it didn't work, But we were missing something. I did that on purpose, of course. In this design, we had a pre-treatment score. That means before they were, as a baseline, you always evaluate people before the intervention because you want to see how it was before and after, right? It's very important. In this design, we had that. But when I was explaining about this data and we were working with this data, I didn't ask you to do anything with pre-treatment. So now we're going to do that. And that's something that we call repeated measures. Repeated measures means that you have, and you could have a pretest or baseline, and you can have multiple measures following up the same people. It is also called paired samples, right? In this case, it's paired samples because we have only 2 measurements. So we have, I don't know, we have one score in time 1 and one score in time 2, right? So for example, in this case, subject number 1 had a score in the post-treatment of 80.72, but before the intervention, his or her score was 36.62, right? Before the intervention. If you just check the values, it kind of looks like they got better, right? And actually, you kind of look at the numbers, right? Look at the score here in the line number 3, right? On row number 3, right? The score of the post-treatment is larger compared to the score in the pre-treatment, right? Before the treatment, right? It looks like they got better over time, right? Regardless of the group. So what we're going to do first is to check if that difference is explained by chance or not. And that's when we are going to use something that we call a t-test for paired samples, right? And as I said, paired mean that, well, they are the same people, right, over time. There is dependency between them. In statistics, when there is dependency between samples, you have to follow a different procedure, right? And you have to kind of interpret the results in a different way. So the first option that you have is a t-test. And the interpretation is going to be very similar to the t-test that you know between groups. Remember that the test that we were studying before was between groups. And probably this topic is old for you. Probably you already studied this when you were in college, I'm sure. Probably your instructor explained you a little bit about independent samples t-test and also paired samples t-test. Right? I didn't add the mathematical formulation or anything here because I wanted to go to the point. How to analyze the data and what is the interpretation of that, right? So in R, you can use the function t-test. And one way to specify that your samples are paired is by using the word pair, right? Very straightforward. And then use this little thingy here, and then you specify that you are modeling only the mean. That's what it says. What we are saying is just take the mean of the post-treatment and estimate the mean of the pre-treatment, get the difference, and tell me if this difference is explained by chance or not. That's what we are testing, right? The null model of these models, of this t-test model, says that there is no difference between pre-treatment and post-treatment. That's the null model or null hypothesis, right? We need to find evidence to reject the null. So the evidence that we have is our data, of course. Our data lowercase, right? That's the evidence that we have. So in the output, you can see that the p-value is very small, right? It's actually, let me see, 0, 0, 0, 0, 16 zeros, and then 22 at the end, right? It's a very small number. So the chance of finding this mean difference by just randomness is very small, right? So this mean difference was not produced by randomness, right? It's hard to find this mean difference in nature. That's why the p-value is very small. So that is telling us that, yeah, there was an improvement, right? It looks like they got better, right, over time. However, we haven't taken into account the variable group. This is only analyzing time 1 versus time 2. That's what we're doing, just taking the mean difference. In many cases, it is fine to do that. If your intervention has 2 measures over time and you want to see the difference between these two, and well, you can do it, right? It's fine. A t-test should be sufficient for that. However, many times in our intervention in psychology, we have other variables that we need to control for. Like for example, in this case, what about age? How do I add age? In this topic matters, right? Age explains a lot when you are talking about dementia and decline. And I'm not able to add age here. I can add only 2 scores. That's the only thing I can do in a paired test. It's a model that is good, but it's not the best, right? So what should we do? Well, as always, we can always do regression. And especially in this design, we need something more appropriate, right? Because this is something that we call what some people call it in experimental science. We call it a mixed factor model. Why mixed? Because you have a factor that is within groups, which is time, right? Time 1 and time 2. That's something that we call a within factor. And you have another factor that is between groups, which is group A, B, C, and D. That's something that we call between. So you have a experimental design where you have a within factor variable and a between factor variable, right? So you need to analyze both in the same model. Never analyze both components in a separate models. You will get totally wrong conclusions. They have to be modeled in the same model all the time. They have to be added in the same equation. Now, look at what I did here. In this case, let me show you the syntax. By now, probably you're familiar with regression, how we write it in R, probably you still remember that. I hope the break didn't delete anything on your brain, in your minds. Hopefully not. But it's okay if that happens. You will remember. So in here, we have the function LM, that stands for linear model, right? We are doing a linear regression. And look at what I'm doing here. I'm using the pre-test as a predictor of the post-test. That's the only thing I'm doing. And you might be thinking, well, that looks crazy. Why? Why you are doing that, right? Well, in longitudinal data, that's how we call it most formally. That means that longitudinal means that you have multiple scores for the same subjects. So we auto-regress the scores all the time because that will give us the difference over time in the slope. So in the output right here, we have an intercept and we have a slope. That's the only thing we have because we have only one predictor. This slope is giving you the rate of change, right? And that means that how much they change from the pre-test to the post-test. So you can see that this slope is positive. That means that they really improve over time. Actually, it's telling you that for 1 unit increase in the pre-test, the post-test increased 1.10 units. That's good. That is telling you that yes, there is a change, right? And that change is not explained by chance. We already know that from the test, right? So it should be fine. The intercept, in this case, a little bit tricky because we cannot interpret the intercept because we don't have zeros in this distribution. The intercept is normally the mean of y, in this case, the mean of the post-treatment, when Canton pre is equals to 0. But Canton pre doesn't have a 0. You cannot have a 0 in this test. People will have always at least 1, right, as a score. So that's why the intercept is not interpretable when we do this. However, we can make it interpretable if you want. We could do mean centering, or we can do also, as you might imagine, we can actually transform our predictor into C-scores, right? And I'm using the function scale right here that will change the distribution, well, transform the distribution. It will transform the distribution into C-scores, right? So now I do have zeros in my distribution, and the intercept is the actual mean of the post-treatment. So what is happening here is that it's telling you that people start on average, right? There is the average of post-treatment is 129, right? And what it's telling us is that the difference between pre and post is 27.19. In this case, one is scale, the other is not. So it is 27.19 units, yes, bigger, and compared to the others, to the other mean. So Now it looks bigger because I transformed the data. The slope will be dependent on how you transform that data. So in here, given that I'm using C-scores, and the other one is not C-scored, it's kind of hard, but we can make it both C-scores, and it would be better understood. Let me just do that. I'm going to use a scale right here as well. So both are in the same scale in C-scores. And can use zero here. See the output. Oh yes, very tiny effect. And just so you can see the real number. Well, without scientific notation. Right here. So look at this slope after changing this into C-scores. Now is that correlation. So it's telling us that the difference, the effect size, is 0.76. It's a big effect size. The correlation in a regression can also be a measure of effect size. It is a measure of effect size in this case. So it's telling us that the magnitude of difference between the pre-treatment and the post-treatment. And it's actually big, 0.76. You can also say that the relationship between these two is 0.76. You can also say that. Because what we are saying is the magnitude that they share together, the variance that they share together, right? And it's very big, right? So they really improved. They really improved over time. And look at the R-squared, right? The R-squared is 0.56. So you are explaining almost 60% of the variance on your post-treatment, only by the pre-treatment. And that's okay, and that's expected because they are related, right? They are the same measure over time. If this one was very low, and if the R-squared was very low, I would be worried because you are measuring the same thing over time. So they should be very related, and the amount of variance that you explain should be very big. Now, in the first question right here, I'm asking you to check if what I said before is correct. So what I said in this paragraph here is that when you change Hancock pre and just transform this into a C-score, this intercept is the mean of your outcome. So I'm asking you to check that right here. So it's going to do it. So let's do that. Let me open a new file. I'm going to do this in a Quark file. Okay. Just delete this, otherwise it will go to visual notes. And just copy the first question. It says, check if the mean of Hancock post, right, and the intercept right here, the estimated intercept, are really the same value, right? Use R to check it out. I said R here, but you can also use Jacobi. I don't care, right? If you want to do everything in Jacobi, you can do it. However, there is a point where I don't know how to do it in Jacobi. I'm asking you to estimate the simple slopes and do some plots that I don't know how to get in Jamovi. I know how to do it in R and also how to do it in Python, but I don't know how to do it in Jamovi. There might be a module that you can download. I can show you how you can download modules for Jamovi, and you can try and see if you can find something, and you can teach me where is the module for that. But to be honest, I haven't found how to make it easier for people who are learning stats. I mean, we could do it by hand in Jamovi, transforming the data and doing other things, but that would take a lot of time, and I don't want you to waste your time in that way. But yeah, you can use Jamovi for all the questions if you want to, right? You don't have to use R. So let me just copy this first. And let's call this, well, we can do something like this if you want. And then let's delete everything that we have here, which is a template. Let's insert a little comment here. You will need these pieces of code. Oh, sorry, I didn't mean to do that. These pieces of code to, let me just build this report. Right here, this will open the data, right? I always keep one chunk of code for that, and then for the analysis, I do it in a different chunk. But you don't have to do it like that, but for me, it's more organized. It looks cleaner. And see. So let's open the data again. This session, it's already there, but I'm just gonna run it. And I ask you to check if you can use mean or summary as well. And this will get you the mean. So you can go to auto memory, right here, summary, right, and select by using the $sign, right? It will show you this dropout menu, or drop list. And you can just select Hancock post test and then press enter. And the mean says it is 129.18, and it's exactly the same as the output, right? So when you transform the data in a way that that your predictor has a 0, right? The intercept becomes the mean of your output, right? And you can see the change from the mean if you want, right? Which is useful in many applications, many times when you are analyzing data, interpreting that as well. So what is the answer to this question? It would be, once you show that, or you can put it here, you can say, yes, the mean of the outcome what's the mean? Just copy and paste this. I always copy and paste to keep everything consistent. The mean of the outcome cost is the same as the estimated intercept. Yeah, and that's the answer, right? Oh, and actually, well, I added this table to explain that part. So this is before the transformation, right? Before the transformation, the mean of the pretest was 64.30, right? If I change it to a C-scores, the mean is 0, and the standard deviation is 1. When we transform your continuous variable into C-scores, what you're doing is not creating new data. You're just moving the point where the mean is located. So 0 is going to be your mean. 0 is going to be your mean, and your standard deviation is going to be 1, right? That's what we call the standard normal, right? The standard normal distribution. And by the way, I'm not transforming the data into a normal distribution. That's another thing. And we call it the standard normal because by doing that, it kind of follows this bell shape. But the data is what it is, right? The distribution is what it is. And by transforming this into Z-scores, you are not making your data normalish. You are not doing that. And that's something that I should clarify many times in this class, and I forgot to do it. And why am I saying this? Because I have seen that even faculty say that. Like, hey, I transform my data into Z-scores, now it's normal. No, your data was not produced by a normal process. It doesn't matter if you change it to a Z-scores. The data was produced by a process in nature that was not normal, probably. Right? It was not the Gaussian distribution. It was another distribution. And there's nothing to do about it. You cannot make it normal, right? You can change the shape in a way that it kind of looks like normalization, but still, it was not produced by normal distribution, right? In this case, I don't think my scores are produced by normal distribution, but it's the best model that I have so far to teach, right? So I'm assuming that the normal distribution is the best. Where I'm assuming that in the regression model and also in the t-test. The t-test assumes that the conditional relationship between x and y is normally distributed, right? And regression does the same. So of course, the assumption here is that the best representation of the relationship between x and y is the Gaussian distribution, right? We already know that, but it's the best that we have. Oh, and actually you get that. Nice. In here, I'm asking you to create a histogram, right? Where you're going to compare the distribution of the score before the transformation and the score after the transformation. So let's do that. Sometimes I don't remember what I write. I'm very consistent. And let me just this. Yeah. Now another chunk of code. And let's do first the histogram before the transformation. So this one is going to be the histogram before transformation. Right? You can use the function hist. From base R, you don't have to use ggplot. If you want, you can use ggplot, but it's not necessary. And in here, we are going to use the dataset out of memory. Okay. And this one is the pretreatment before the transformation. Let's see how it looks like. It looks like this. Let me do more breaks. See if I think it won't matter because it's just a few cases. Yeah. So this is how it looks like. Look at that. And that makes sense, right? Because this is an intervention with people high and low of mild cognitive impairment, right? So we have a bunch of people who are healthy, right? Of course, in the pretreatment, you would see that chunk towards larger scores, right? If you have a larger score on the pretreatment, like these guys here, that means that you're healthy. You did all the cognitive tasks right, so you get a larger score, right? You are healthy. People with mild cognitive impairment will be in this chunk because they have a lower score, right? They fail a lot of tasks in the cognitive test. So of course they are here, right? So it makes sense, right? This is before the transformation. Now let's compare this plot with his score after the transformation with Z-scores, right? We're going to do the same. You can copy this, exactly the same code right here. But we are going to use the function scale. This will transform automatically the distribution into z-scores. And just run the code. And it's exactly the same. Of course, it has more beans because now the scale changed a little bit. I just changed the beans, the amount of beans, and the histogram plot. But basically, it's the same shape, right? It doesn't change. It doesn't have to change. I didn't create new data, right? I just transformed the mean, which is 0 right now, right? And yes, it looks like polarized. Because, yeah, we have people with very high scores and people with very low scores. So it makes sense. So why did I ask you to do this? Just to make you realize that we are not creating new data. It's exactly the same data. We are just transforming data from one distribution to another. And you can also create a density plot. And we can do it here. You can convert the density plots. Let me do it here. Let me just close this. And let me see. Oh, I will need to do extra steps here. And I will need to do that. It's fine. Right later. I don't want to complicate your lives. I already did too much complicated things for you. So yeah, that's the answer, right? The answer is, and actually, let me just do it here. Histogram after transformation. And in here, you can say that the conclusion is z-scores. Or actually transforming changes distribution into z-scores will not change the shape of the original distribution or original values. Right? Just like that. Let's save first. Same template. Okay. Now okay, now in question number 3, if you want, you can copy the code and do it in R, or you can just run it here. If you see run code, you can run it on the website, right? And let's see what it says, right? And what I'm asking you to do is to add group in this model right here. The variable group is exactly this variable right here. And do you know how to do it? How do I add that variable into the equation? In R syntax, of course. How do we do it normally? Come on, we have done it several times. We have done this adding and removing variables, right?
Plus.
Plus group. Yes, exactly. Yeah. So let's go here and do it right now. And then let's run the code. This is what happens. Now we are taking into account groups and change over time, both at the same time, which is wonderful. Now, there are things to notice here. Now it's telling me that the change over time is 2.28 units. So it's telling me that for 1 unit increase, for 1 unit increase in the pre-treatment, the post-treatment increases 2.28. It looks even bigger, the change, right? When I take into account the groups. That change that is telling me looks like explained by chance, right? Because of the rule of the p-value. Remember that if the p-value is less than 0.05, the ugly rule of thumb says that we should say, hey, this is explained by chance. But it's only 0.6, right? Well, you could round it to 0.7 if you want to. It's still a very, very, very small chance of finding that mean difference in nature, right? It's still small. It's not less than 0.05, which is the rule, but it's still very small. I would count that p-value as a p-value that is telling me that that estimate is not explained by chance. I would do it because the rule of thumb of 0.05 is not something cast in stone, and it shouldn't, right? Also, I would pay attention to the confidence intervals right here. Well, they're kind of big. They're very big confidence intervals. That's a problem. And they are very big because we don't have a lot of people in this data. And this data set, I believe we have, let me see how many we have. We have only 40 observations. So the confidence intervals are very big, very wide, right? It's telling me that the real mean difference could be a number between -15 and 4.71. It's a lot of numbers. There is a lot of uncertainty in the estimation. But that happens because I need a bigger sample size, right? But it's fine. I already know that. Now, we have extra estimates right here, or extra coefficients. We have this little thingy that says group B, C, and D. Why? What is that? Or can you tell me what is the reference group in this equation? You remember, it was 4 groups, right? So what group is missing there?
One group.
Group A. That's a reference group, right? Because this is a nominal variable, so we need a reference group. So what we are doing in the 3 last lines is to compare the mean of group B versus group A, the mean of group C versus group A, and the mean of group D versus group A. And you can see that it's negative. So it's telling you that after keeping your change over time fixed, that's how we interpret this. After keeping the change over time fixed, right? The difference versus group B is, well, the score versus group A, sorry, is way, actually, oh yeah, smaller, yeah. So it's telling us that, group A, yeah, it's totally healthy. Oh yes, they have a lower score. That's interesting. I didn't see that coming. So yeah. So what it's telling us is that the score in group B is lower compared to group A. Group C has a lower score compared to group A, and group D has a lower score compared to group A, right? And group A is the healthy people who got the treatment, right? Yes, right? Oh, that's interesting.
Unhealthy people.
Oh, healthy, yeah. That's weird. Let me check something. That's why I'm confused here. Yeah, it was mild cognitive impairment. Oh, that's weird. Why? I'm getting this. It's interesting. Wait a second. Why? Oh yeah, no, that's fine. That's fine. Yes, yes, yes. No, that's okay. That's okay. That's totally fine. Yes, it's telling us that the reference group has the lowest score. Yes, that's totally fine. So what is happening here is that all they are negative because the reference group have a very small mean, right? So what is doing here the model? Let me explain you. Probably here in R. What it's doing is taking the mean of group A. Let's imagine and it is 23, and the other group, I don't know, is 52, right? So you will get a negative score, right? If your group reference, which is people with cognitive impairment who didn't receive the treatment, right? Or they receive it, they get it. Check. They actually, oh, that's even worse. Yeah, it's telling us that actually the intervention didn't work at all, right? It doesn't matter the group they belong. The change that we observed right here, pre and post, it looks like it was just because the time went by. That's why there is a change. Just because people were getting older. That's only what happened. The intervention didn't work, right? Because if that worked, we would see that they got better, and you would see a difference, a real difference. For example, between group B and group A, right? But it's telling me that is actually they are worse. These people didn't get the intervention, right? And they actually had a larger score.
So if it did work, it would have been a positive number?
Exactly.
Okay.
Especially group B, because
Yeah.
group B is their peers.
Uh-huh.
Group B are the people who have cognitive impairment, but they didn't receive the treatment, right? So if they didn't receive the treatment, that means that group A should have done better, right? And this is low, should be positive, right? That means that group A got better, right? Got a larger score compared to group B, who didn't get the treatment, right? But that didn't happen. What happened was, and actually, let me show you the means, probably with marginal effects right here. Let me show you here. Very quickly. Let me see if I can get it. Something funky for fun. And let me check something very quickly. What's it in here? It's just I don't remember the function. I'm looking for the function, that's why. The exact function for that. So now we can see the predicted mean for each group. So look at what happened, right? So group A is actually very similar to group B, to be honest, right? and there is no change between them. And there should be a change. If the intervention worked, because A got the intervention, this mean should be around here, right? So if I get this one to work, so let's imagine that it should be around here, right? That would show that there is a difference with group B, but that didn't happen. It's flat, right? And actually the model says that the difference is like 0.16, right? Or 16 units, I don't remember. And look at what happened here, right? These are healthy people. These people got the treatment, and they are actually worse than the people who didn't get the treatment, which is weird, right? Even if you're healthy and you get the treatment, you should be a little bit better, but that didn't happen. The most control group is this one, healthy people who didn't get the treatment, and they actually got better. Look at that, right? So what is happening here? Yeah, the intervention was chaos. It didn't work at all. And that happens when you are learning how to do research. I kind of do this, you know. It was a little bit of money that I threw under the toilet, I guess. I learned a lot. And actually, when I analyzed this data, I saved this data for years because I thought, well, this was a waste of my time. And then I realized, you know what? Oh, I can teach with this. So now it's teaching material, right? But yeah, the intervention didn't work, and there were a lot of mistakes. So I can tell you, drinking a coffee or a beer. But in general, yeah, didn't work at all. That's why I got confused with the regression. It was like it was really that bad, but yeah, it was that really bad. So let's come back to the output right here. Where it was? Oh, let me delete all these things that I draw. And then we come back to presentation here. Here. So yeah, after controlling by the change over time, these are the main differences versus group A, right? So of course, group B is way better to group A, right? It's telling me that group B is 61.38 points larger compared to group A, because they're healthy people who, yeah, didn't have intervention, and this is the main difference. But there is a thing here, and the thing is that all these mean differences are explained by chance, right? That's even worse. It's telling you that everything that I did can be explained by chance. All the work that I did in these sessions with my advisor back then didn't work. It was a lot of hours talking with these other adults doing sessions, and it didn't work at all. And they got better just because they got older, and for some reason, some of them got better. But I don't know why, because I don't have enough information in this data set right now. I do have more variables in the raw data somewhere in one of my clouds that I was using back then. But I don't know where they are, what is the raw data anymore. But yeah, the final conclusion is that one. So in order to answer the question, which is the most important thing here, it says modify the following code and add a variable group. Interpret the results. So how do you interpret this? When you go to Jamovi, when you go to your quarter file or Word file, right? And let's do question 2, right? And this is 3. Ah, yes. No, I mean the previous one was 2.
Yeah.
Ah, yeah.
The one we're on is 3.
Ah, yeah. Yes. Let's come back here. And if you do it online, you can take a screenshot of this and just put it there. Or if you want to run this in your session, you can do it. right, in your hard session, in your local computer with Quarto, you can just copy the code, right? It's up to you. And I'm gonna use, in order to get a beautiful output, I use parameters, right? You don't have to use this package, but it displays the output in a tidy way, and I like that when I'm teaching. So we have group here, we already added group, right? And then we can get the estimation, and the interpretation is, for instance, right here, you have to interpret this first slope right here. So the interpretation is as follows. One, increase in the pretest, the post-test score increases 2.28 units after keeping group fixed. And you might be thinking, well, what does it mean to keep everything or something fixed? In regression, what we have is a multidimensional plane. If you add more variables, it gets complicated, right? It's a multidimensional plane. And when you add a variable into the equation, you are taking into account the variability of that variable. And when you take into account that variability, we say that that variability is fixed, is explained by the model. It's not something that is out of the model and it's just a maybe. It's already there. So what we say is we are explaining the change over time after controlling by or by keeping fixed the grouping membership. If you have H, it would be the same conclusion, right? You would say this is the slope or the change over time after controlling or after keeping fixed H, right? Because H is part of the equation. And here's a maybe. Probably H is explaining something. I don't have H in this data set. I should have it, but I don't have it. So it's very likely that there are other variables that might be explaining why it didn't work, right? I should come back to my old files, but you know, this was done in 2010. So you might imagine that I don't know where it is. And I was not that organized when I was very young. I was naive and crazy. Yeah. No, I wasn't crazy. Well, maybe a little bit. But I was very responsible. I mean, I executed the whole research project and I was an undergrad. So I think I did a good job at least learning how to administrate a research project. But I totally made a lot of mistakes. But yeah, so that's the interpretation that I wrote here, right, for the first slope. Now let's see this slope that is actually the mean difference versus group A. So the interpretation would be like this. And the mean of group B. Actually, let's change this so that makes sense. Oh, the mean difference between group A, group B is minus 16. 16. Mm-hmm. 16. And it is not, and it is explained by chance. It is explained by chance. Because the p-value is greater than 0.05, right? And the same applies for the other groups. It's the same word, right? And I forgot to add here actually something about and storing the 2 pointer after keeping a group fixed. This slope is not explained by chance. Because the p-value is actually 0.7. So you might be confused, as I said. It is not smaller or less than 0.05, and I'm still saying that, right? And as I said before, I'm doing it like that because, in my opinion, 0.07 is still good evidence that that estimate is not explained by chance, right? It's still, I have only 7% chance, or 7% probability of finding that estimate in nature. This is still a very rare estimate. It's a very rare mean difference, right? So I would call it still not explained by chance, and I would justify that in my in my publication if I was going to publish this, and I would fight with the reviewers for several years until they allow me to publish something. So yeah, I would do that if my data was the crap like this one. This is not the best data, but I guess it's also a good example of that. Like, things don't go like expected many times, and you're learning, and that's fine. I feel bad for the participants. I always think that a publication honors their time, but I couldn't do that with this. But at least it trained me as a researcher. What else? Yeah, those are the answers for this one. Number 3. Oh, and I skipped the break. Do you want to finish early today? Yeah, right? Yeah, I know that. Yes, let's finish at 11:30. Let me just continue with one more question. Now, this is the section that I had for repeated measures, right? It's just an example, a very, very tiny example of what you can do when you have at least 2 measurements. When you have multiple measurements, let's imagine that you are doing a research with exercise, and you want to monitor the heart rate, using a smartwatch. Like nowadays, we do it in research projects. We have tons of data. Like many of you are using smartwatch right now. So that's tons of data every day. That's something that we call intensive data. There are other methods to analyze that data, right? Very similar to the foundations of regression and t-test. Actually, those are the foundations for models to analyze that type of intense longitudinal data. But of course, we cannot talk about that here because that would be very, very advanced. And I think you are still digesting what I did here. So if you ever have that type of data, or you want to collect that type of data from participants, and for example, those who are taking seminars with me, and for some reason you find a way to ask people for the data from their smartwatches, we could do analysis like this. But normally, people don't know that they can download the data from the website of your smartwatch, and you could analyze the trends of your physical activity and see if that change is because of chance or not. You could do that. There's something that we call time series analysis, and it's very fun. I always want to do that with my data, but I never have time to show how you can download the data from your smartwatch or your account. I mean, if you're using Apple will allow you to download the data that you have. Garmin, Fitbit, they all have your data, and you can just download the data from your profile. It's kind of nice. And I want to do it because I always want to improve my physical fitness. So I want to see if my changes actually are causing a change or not. All right. Now, in this part, it looks fine. Can you read that? Oh, yeah. Nice. And I also like Sponge. SpongeBob. Nice. We didn't have time to practice more about moderation, so I added another problem about moderation. But this time, we will walk slowly through the process of interpreting a moderated effect, right? For this part, you can use Jamovi, as I'm saying there, but there's a point that is going to be complicated for you if you want to estimate the simple slope. Not simple slopes, but the part of plotting everything in Jamovi. I don't know how to plot that in Jamovi. I guess I would have to estimate, but to get the predicted values and do it by hand. But I don't want to. I don't want you to get there. So let's pay attention to the question number 4. It says estimate a classical regression model where I forgot to tell you, and actually I should explain that. This is the OUS dataset. Remember the dataset where you were selecting the best model, right? And we had physical fitness and variables related to older adults, right? Older adults were part of this. It was another study. It was not the same study that failed, of course. This one was better, and this one actually had very good outcomes, and we did better. And especially because Kansas was helping us, so we had more equipment. So it was Costa Rica and Kansas. So of course, your University of Kansas has plenty of money, so we did better. But in this one, I believe, right, and actually I have a strong belief that the score on block design is explained by your oxygen level, right? The maximum oxygen level that you can take. Well, not you, other adults, right? I also believe that the Stroop color task is related to the score of building blocks. And let me remind you what is the Stroop test, right? It is important in order to understand why I believe that. So remember that the Stroop test, actually Wikipedia might have it here. Oh, wait. Yeah, I know that. Sometimes I don't. So it's something like this, right? You have to say the color without reading, right? That's one of the parts of the Stroop. Actually, the Stroop test has different parts. The first part, you have to say, well, it's just black and white letters, right? With red, blue, and you just have to read the letters, right? After that, in the second part, you have to say, to read the words. In the final part, is like this. You have to say the color of the letter, not what it says. And you might be thinking, well, that's easy. Well, it's not that easy, right? Because we learn to read, and we are prone to read. So, for example, in the second part, the colors don't match, right? So, for example, if I tell you to say green, your brain is like, I want to say purple, right? In the second part, because the color and the word don't match, right? So that causes an interference. So that interference is handled by your working memory. Your working memory is trying to hold the right instruction. I should read the word. Well, I should say the color, sorry, not say the word, right? It's kind of hard. And especially if you are an older adult with cognitive impairment or some symptoms of dementia, it's even harder, right? So this is a good test. Well, it's not a good test. It's one of the possible tests that you can use for measuring interference in your mind, right? In your cognitive performance. The other one that I believe is a predictor, of course, is VO2 peak, and the outcome is block design from the WISE test, a Wechsler inventory scale, right? And as you might remember, it looks like this. Let me just show you one. We go to pictures. Like this, right? So the participant will see a model, right? A printed page with a model, and you will give to the participant a lot of cubes with different patterns. And they have to replicate the same template that you give to the participant, right? So in this case, the participant had to replicate this one, and actually he or she did it right here with the blocks. and there is a time for that, right? And again, you might be thinking, well, that shouldn't be hard. It's like a puzzle, right? But it's way hard. It goes by levels, right? There's a point when the pattern has a lot of tiny patterns, and you have to do it in a very small amount of time, and you get nervous. You get anxiety when you are evaluated. That's another thing, right? You have to handle your anxiety as well when you're evaluated and watched by another person, right? So it's kind of hard. Even when I tried, I did a good score, but I didn't get to the final cube. But then I can do it again. See what is my timing now? But that test is also a good measure for dementia, right? We always use it for screen dementia as well. Let me come back there where it is. Let me check if I have questions online. So as I said, I believe this could be the outcome, right? For this next part, you will need to copy and paste this code where I'm reading in the data, right? You can do it here. Actually, let's go to RStudio. And actually, this is question 4. You can copy the question later, you know. And we are going to use this piece of code. By running this, you're already reading in the data. You can see it here in the environment. Just pull up a little bit here. The object is right here, OUS data. You can change the name if you want. I just call it like that. But you can use any name. And now I'm asking you to estimate a model with this characteristic. So this variable, block design, will be our outcome, right? So let me copy that. Here, I'm going to create another chunk. So the model is going to be saved to mod, just for fun. And my predictors are VO2 peak, which is the amount of oxygen, and stroke color, right? So let's do that. When I copy this, because they are exactly the same name. And stroke color. And the data is OUS data. Okay. And we need the function summary or the function, whatever you want, model parameters from the package parameters if you want a tidy output. Okay. And let's see the output. This is nice. This looks nice. So it's telling us that for 1 unit increase in oxygen, your score in block design goes up by 0.44 points, right? So it's telling me that if your physical fitness is better, your score in the block design is better. That's what it's telling you. That's nice. So I was right. The level of oxygen is a proxy for cardiovascular fitness. That's the point. Because you might be thinking, why oxygen? Why do we care about the amount of oxygen? Well, because that's a measure of your heart. How good is your heart, right? So given that we cannot use an electrocardiogram, right? Like putting people into a machine and just measure their measure other things about the heart because that's expensive. We use a measure that is less expensive, and we can make conclusions as an approximation to that. We always do that in science, depending on how much money we have. So VO2 peak is an amazing measure to make conclusions about cardiovascular fitness, right? So yeah, if your heart is good, if your physical condition is good, you will get a better performance. Also, there's another thing. It's telling us that I was right. When people are good at filtering out interference, they also get a better score in the block design task, right? It says that for 1 unit increase in the score of stroke color, the block design score increases by 0.36 units. So yeah, it's getting better, right? And that's what I was expecting. And the p-value says that these slopes cannot be explained by chance, right? They are not explained by chance because the p-value is less than 0.05. So yeah, I was kind of right. So how do you answer this? Well, you just need to add an interpretation here, like the one that I just said. From 1 unit increase in this variable, this one increases by this amount of units, right? This is how we interpret the slope in a regression model. And I use units because, for example, the metric or the range of values for VO2P is totally different from the score of the block designs. So if we want to make a better interpretation, a standardized interpretation, you have to transform the solution into Z-scores, right? You have to transform your variables into Z-scores. And actually, you can do it right now. If you want to see that into Z-scores, the fully standardized solution would be achieved by just using the function scale. You don't have to do it in your dataset. It can be on the fly, which is nice in R. And now you can even compare, which is good, which variable it has a bigger weight in the explanation, because both are now in the same scale. So as you can see, stroke color is actually more important because it's telling you that the relationship between stroke color and block design is 0.40 after controlling for the level of oxygen, right? So look at that, it's 0.40 and the other one is 0.16. So now you can compare both. Now you know which one is more important in terms of the weight that they have in this equation, right? Because I transformed everything, right? So yeah, VO2 peak is still important. Of course, I wouldn't delete that one from the equation. But of course, stroke color has a bigger weight because it's a paper and pencil measurement, and also we already know that stroke color and block design are part of working memory. Both are measuring a similar construct that we call working memory. So they are related, and they should. And that's why I did it, because I knew they were related. When everything is standardized, let me just write down the interpretation. When you have a fully standardized solution like this one, you can say for 1 standard deviation in VO2 peak, and the score of block design increases 0.16 standard deviation. When the solution is fully standardized, that's the interpretation. And the same applies for stroke color, right? So we are talking in terms of standard deviations, not about units, right? Or in simple words, we actually did a partial correlation. That's what we need there, right? So this is the correlation. 0.16 is the correlation with log design after controlling by the structure, right? Questions so far before we finish today? Good.
Just because, if we didn't do that part of the standard deviation, you said for one, without that, like the first, model that you brought up, it would be 1 unit increase in the variable?
Yes, exactly.
Okay,
Yes, because they are different units. So we can only talk about units.
okay.
We
And
don't
the
have
other
a
one
common metric.
is, okay,
Yes.
the full standard deviation is.
Exactly. If we were using kilometers and everything, we would replace unit by kilometers or miles, right? But we don't have that here. And that's the case many times in psychology. Our measurements are crazy, are insane. That's why people from econometrics are like, man, you're just insane. You're creating mambo jumbo things here. They don't understand how we measure things. And actually, we have a lot of fights sometimes with econometricians. And some of them are very right. We should make our effort to make better standardization of our measurements. Otherwise, it's just pure chaos. We need to standardize our measurements, but that's something that will take several years. But if you don't have questions, I let you go. We will continue with this on Thursday, right? Hopefully, we will have time after my friend Larry comes here and explains his project and invite you to be part of his internship, right? So, yeah. So,
Can you see the RP for the scale adjustments?
yes, of course. This one right here? Yeah. So